Hello, my name is Darren Sakala. I worked with Tyler Skeen on this project for ECE 574, Advanced Software Techniques and Engineering. So today I'm going to be demonstrating my project and the general overview of how it works and where each requirement is traced to. So for a general overview of our project, what we did was we designed a smart home system to monitor the temperature inside and outside of the house, as well as monitoring the water level of the soil and tracking current forecast information for a given location. So for the general overview of the hardware portion of our system, we have a Raspberry Pi that's connected to two different temperature sensors. These are the DHT11 temperature sensors here and here on the breadboard. And we also have a water sensor, which is a VMA 303 sensor made by Velleman. The VMA 303 sensor directly connects to an analog to digital converter, which is an MCP 3008, and that connects to the Raspberry Pi over SPI. The two temperature sensors connect just over standard GPIO or UART. Everything here is powered by a max of 5 volts and resistances are handled accordingly. Each board or each breakout board of each chip has short protection and other sorts of resistances on there. So for the focus of our project, what we really wanted to do was to implement the V model on a very small scale project and see what the results were. We essentially had a modular design of 3 core modules, the first being the temperature controller, and the second being the water controller, and the third being the GUI of the system. So I'm going to give you a basic demonstration starting now. And so what I'm going to do is run main.py of our script. As a starter as well, everything was written in Python. So what it's doing now is it's initializing all the modules, and here we have our GUI. So what this is demonstrating is it's demonstrating the forecast for the next 12 hours here, as well as the current weather information here. And we also have the forecast for the next 5 days. So you can see that tomorrow it's going to be 32 degrees and cloudy, whereas at 3 a.m. tonight it's going to be a clear night, but it's also going to be 21 degrees. There's pretty much no chance of rain for the rest of the week as well. Tomorrow there's about 30%. So you can see here, these are all of our system states as well. So the outdoor temperature sensor is currently not being interfered with at all based on our heat source or our cold source. So it's measuring about 68 degrees. This is fairly accurate with the temperature of the room that I'm in right now. Humidity is a little high, but we are in a basement, so it is going to be more humid. Then the indoor temperature is a little bit lower because it's not in direct contact with our heat source, therefore it's about 64. You can see our recommended temperature based on our algorithm is do nothing at 68 degrees. And so this is basically setting back the outdoor temperature as what you should set the thermostat to. Our moisture level here, so we have a dry cup of dirt that it's currently inserted into, and you can see it's reading 0.0%. We say that the water level needs water, and that we should also turn the sprinkler on in this scenario. So what I'm going to do is I'm going to take the water sensor out first and insert it into our wet dirt, which is basically mud. And then after a few seconds of reading, it should be able to generate on the GUI that we have a new reading. And so you can see in this very wet dirt, we have a moisture level of about 40%. And based on research that we've done online, we were able to determine that an acceptable range for normal dirt in Michigan is about roughly 15% water capacity. Anything above that is oversaturated, and therefore you shouldn't water the system. Therefore we say the water level stays okay and that the sprinkler's off. So now for a little demonstration of our temperature system. So we have our outdoor sensor here, and for now I'm going to move it into the path of our heat lamp here. And so you see that slowly the outdoor temperature is going to increase. For demonstration purposes, we set the time on the Raspberry Pi to update at a rate of 3 seconds. Our normal update rate would only be 10 minutes. Therefore, this is just for demonstration, but for right now, everything's updating at a rate of 3 seconds, just to make it seem faster. You can see here that it jumped by a degree, so now it's 69.8 degrees. It's going to take some time to get calibrated, but it will slowly get up to the point that it needs to. And then as well, if we take him, you can see it's at 71.6. If we take the temperature sensor out and insert it into here, our cold area, it will also decrease probably around 60 to 55 degrees, but it's going to go slowly because of the filters that this sensor outputs, and it's the filters that are implemented within our system. Those are built in to protect against things like instant shock. So if all of a sudden you're reading 70 to 75, and then it's like, oh hey, here's a value of 20 degrees, it's probably going to throw that out. And the APIs that we use to read from the sensor take all these into account. And so you can see here that our outdoor temperature is slowly going down now that our sensor is in contact with the ice. And that will conclude the demonstration of our project. And I will begin next with an overview of requirements and where each of these components trace to which requirement. So as I mentioned earlier, I'm beginning a brief overview of the requirements and how each thing that I presented in that demo traces to each requirement. So for some of our disclaimers, obviously we were really constrained by time and by money, and since we were both of us programmers were working full-time during this semester, we were only going to focus on a select few components to design and release. This really is a software prototype, and really the focus of our project was on the software engineering process as opposed to the actual implementation of the project itself. So that's why we went with something a little more simple, and we didn't actually interface with, say, a sprinkler or a thermostat. Just because of the added complexity and the time constraints, this really led to the project that we chose. We did end up designing the system in such a way so that these flags were generated, and using those flags later on, we can actually interface with a temperature with a thermostat, or with something along those lines, with a water sensor or a water sprinkler system. So we really set it up that way that we could use that in the future. And then in addition to our constraints, we did use entirely open source tools and software. There was no closed source implementation that we used. Everything was available online from either GitHub or some Linux repository. Everything, or PyPy was a popular one that we used as well. The central components did operate in a dry indoor environment. Obviously, if you're putting that temperature sensor outside, it's going to be in a little more volatile. The temperature is changing a little more often, but our temperature sensors were able to withstand that, and so that wasn't an issue for us. The system had a cost of no more than $150 to $150. Yes, if you look at the bill of materials in our report, you'll find that it costs $75.75. And the system should be designed and released in less than 2 months. Yes, it was. We really got the ball rolling on our project right around the end of the midterm, and that was when things started to really pick up for us. So for the functional requirements, we needed to set a control flag to water on days that don't rain, set the control flag to water when the moisture level is low, set flags to maintain comfort level based on external temperature, internal temperature, and the weather forecast, and accurately read sensors with a range of 10%. So if you remember in the demo, there was a little bit of delay with reading the sensor, but that's probably because we were reading it so fast. So we would say that this requirement was met because, based on our testing, we were able to determine that the temperature of the basement was about 67 degrees, and as you can see, we were measuring about 68 there. The control flag to water on days that don't rain, you could see when we switched the pins over from one to the other that we were actually able to, when we switched the water sensor from the dry dirt to the wet dirt, we were able to actually read and say, okay, the dirt's now wet, we no longer need to water. And since it's not raining tomorrow, then therefore we were able to water. We also disabled the season feature for that module for demonstration purposes, but there was a season feature there as well. And we also were able to maintain the comfort level based on the external temperature. You can see that when we had moved the temperature sensor from the heat lamp to inside, that the set temperature was actually changing. For performance requirements, calculate changes to make every 10 minutes. Yes, we were able to do that. As I mentioned before, we were reading things at a rate of 3 seconds just for demonstration, but our actual system is going to operate at 10 minutes of an update rate. Make changes within 30 seconds. Yes, you could see in the demonstration that our update rate, when it was 3 seconds, the set temperature would then update about 5 to 10 seconds after that. So it was an update, able to update in 30 seconds. Warn users of error within 5 minutes. Yes, it will. A little error icon will appear in the bottom left when a sensor read error has occurred. And I didn't demonstrate that, but it will do that. For the API interface, we do have So the system should make requests to an external API to retrieve weather data. Yes, it does. It interfaces with the Dark Sky API. API requests are made twice daily. Yes, they are. Weather data should be stored and organized. Yes, they are. If you consult the design document in our final report, you'll see that the weather data is organized into a class structure where we get specific subsets of variables, and they're organized really neatly and for the processing that we need, at least. For sensor interfacing, it does interface with a temperature sensor and it does interface with a moisture sensor. And so those were the two things that I explained earlier, where we use ADC and SPI for the moisture sensor, and we use just standard GPIO for the temperature sensor. For the temperature control, we take two inputs, one from the indoor temperature sensor and one from the outdoor temperature sensor, and we are able to adjust the internal temperature settings of the house. So the temperature sensor settings were actually there on the screen, and you could see that just based on our general algorithm, we were able to change the setting of the temperature based on whatever the outdoor temperature was reading. When the weather's colder, the set temperature should increase. When it's cooler, it should not, and then it should not change. This is defining our comfort zone. So the comfort zone is defined as a 5-degree tolerance beyond. So the set temperature plus or minus 5, the system will kick on if the indoor temperature then exceeds or falls under that comfort zone. And our system also does have a night setting that adjusts the temperature based on whatever the current setting is. So this was hard to see because we were filming this at night, but when the setback occurs, we actually set it back 2 degrees based on the fact that it's night. And we define night as being between 9 a.m. and 9 p.m. or between 9 p.m. and 9 a.m. in a given day. In hot weather, the temperature will increase, and in cold weather, the temperature will decrease. So the set temperature in the summer is about 75 degrees. It wasn't shown, but once it gets to 75 degrees, that will then be its constant state and temperature that it sets at. And then when it gets to winter, 65 to 68 will be its approximate range, depending on the time of day and depending on certain external factors as well. For water control, we do take input from the weather forecast and we do take input from the moisture sensor, and we also call for rain, or since rain was not called for in the forecast, then we are able to water the lawn. You can see that when we inserted the soil or the pins into the soil where it was dry, that it said yes, we should water. When we inserted into wet soil, it said no, we no longer need to water, the soil's okay. And then so the temperature never reached below 50 degrees Fahrenheit, but it actually would cut off the water module entirely when it's during the winter and when this condition is reached. So when it gets to 50 degrees, it will no longer water the soil regardless of any external factors or dryness or anything along those lines. And then for the GUI, you actually were able to see that we have system information available. So whatever the temperature control module is outputting, whatever the water control module is outputting, it also displays weather information, the current weather information, as I had explained. It also displays information about the forecast for the next 12 hours and the next 5 days, and it also displays current system statuses.